Welcome to week 2. Last week we just reviewed. This week we're going to move on to a very powerful tool, the ideal gas law. And it works as long as the gases behave according to the kinetic theory. And we talked about that. You filled out that sheet on it, which means that the gas molecules need to be very, very small, and there need to be large spaces in between them and no interaction when they bounce off. This actually works best with the noble gases because they don't want to interact with themselves or any other molecule. They just go right on by, and if they collide, they just bounce into each other and bounce off. There isn't any kind of interaction. And the gas molecules move in a straight line until they have a collision, until they run into either a wall or to another molecule. Otherwise, they're not affected by other things. They just go in random straight lines until they get redirected. Most gases don't act exactly like this, but they are close enough that the mathematical equation works, and it's within all of the calculations are within like 95% of what the predicted is. For most gases, and the gases we're going to talk about, it'll be much, much closer than that. But sometimes if you have really large molecules and if you have them at really, really low temperatures where they're going slow enough that there is some interaction, then they start to deviate from the ideal gas law. But most of them are going to follow it fairly closely. Now we know that this is a sign of proportionality, that volume is proportional to moles. If you have more moles, if you have more of a gas, it's going to take up more volume. That just makes sense. We also know that it's proportional to temperature. If you increase the temperature, the particles move faster and they're going to spread out, so it's going to take up more volume. You heat up a balloon, it's going to expand. We also know, that volume is inversely proportional to the pressure. If you increase the pressure on a balloon, it's going to shrink. If you decrease the pressure, it's going to expand. So it's proportional to 1 over the pressure. So we know that volume is proportional to the moles times the temperature divided by the pressure. Now, we don't really want to work with proportionalities. It helps us write out sentence answers, but not actually get a number that we can put in a little box that says, hey, this is the right answer. So we want to turn it into an equation. Just like in geometry, if you have the circumference of a circle and the diameter, the circumference is proportional to the diameter. As the diameter gets bigger, the circumference gets bigger. But it's just a proportionality until you use a constant, the constant that we call pi. Then the circumference equals pi times the diameter. And we're going to use a constant as well to turn a proportionality into an equation. So if we start with the proportionality that volume is proportional to NT over P, we can change that into an equation by using the universal gas constant, the R, capital letter R. And if we rewrite this, just do the algebra on it, which I know some of you are really comfortable with, some of you don't like the algebra. We're going to try and take some of that out, do some of that for you. I should say that you should probably, if you don't already, pause the video, and we haven't gotten to any yet, but you're going to need your formula list that you can use. Obviously, you can go back and watch this, but you don't want to have to go back and watch a video and scan through it to find the stuff you wanted on that formula list that you had. Just keep writing formula lists on there because it'll all be in one neat place. Hopefully it's neat where you have it. But if we just rewrite this for R, R is going to equal pressure times volume over the number of moles times the temperature. And the value that you get, now you're going to get units on this, and constants usually either have no units like pi, or they have nonsensical units. I mean, if we look at this, pressure is going to be in either, let's just say it's in atmospheres. It'll be atmosphere times liters divided by moles times Kelvin. Atmosphere liters over mole Kelvin doesn't make any sense at all, but it makes the units work for all the rest of the equation, and a lot of times that's what constants do. They're very helpful, but the units don't make any sense. Now, what is the value of R? Well, you could calculate this for anything and you could come up with it, what it is, but it comes out to, and there are two of them. Well, there's more than two, but we're going to use two. 0.0821, and this is something that you're going to need. And you could use this. We're going to go through, you could put that one down. That's not the general form for the ideal gas law, but it is one form, and it's a very helpful form. But you could have down that R equals that, and that's if your pressure is in atmospheres. Now, if your pressure is in torr, then you use this one. So it depends on, you just look at the problem. Are they giving me the pressure in atmospheres? If they do, then your number for R will be 0.0821. If they give it to you in torr, then it'll be 62.396. It doesn't really matter as long as you use the right R. It gets tricky when they ask you for pressure equals nRT over V, and you know all the other stuff, and you think, oh, which R do I use? It doesn't matter. Then it's up to you. If you use this one, then you'll get a pressure in atmospheres. If you put this one in, then you'll get a pressure in torr. And it doesn't matter. Both of them can be equally right. Just make sure that you write the right unit after the pressure. So if you get 1.2, make sure you tell me that's atmospheres. Okay, or if you get 890, tell me that's torr. So it doesn't matter which one you use, but it does. Students often find that tricky when they have to solve for pressure. Whichever R you put in, that's the unit that you're going to get out. And there's no secret between how are these. There are 760 torr in one atmosphere. So if you just take this times 760, you'll get this. Divide this by 760, you get that. So it's just the relationship between atmospheres and torr. Okay, so this is the traditional ideal gas law form, PV equals nRT. But we're going to just help those of you that really don't like the algebra. We're going to just quickly write this. What if we solved it for the others? Now, we don't really need to solve it for R. We already did, but the R is given. We know what the R is. So we're going to solve it for the other variables, and we actually already did for V, but we'll do it again real quick. Remember when you use this that the pressure needs to be in either atmospheres or torr. And also remember that millimeters of mercury are the same thing as torr. That's what Mr. Torricelli used. He used millimeters of mercury, and then later it was named after him. So sometimes they still give you the units in millimeters of mercury, exactly the same thing as torr. The volume must be in liters. Temperature, as it always has been, must be in Kelvin. And as far as liters, because sometimes a liter is fairly big compared to what you get, remember that milliliters divided by 1,000 equals liters. So if they give it to you in milliliters, divide it by 1,000, and that'll give you liters. Those of you that aren't adept at moving things between different units probably want to put that one in as well. Okay, some other variations, and you can write these down so you don't have to do the algebra on it. It's already done for you. If I'm solving for pressure, we did that one just here, pressure equals nRT over V. If we're solving it for V, V equals nRT over P. If we're solving it for moles, moles equals PV over RT. And again, R we're not going to have to solve for, but sometimes we do solve for temperature. Temperature equals PV over N times R. And remember, the temperature that comes out of this is Kelvin, and that's okay. You can record it in Kelvin, just make sure that you put a K afterwards. Don't just put a number in, or, well, it must be in degrees Celsius. Just put that. No, you can change it to degrees Celsius if you want. Just add 273, or subtract 273, I'm sorry, and then you'll get it. But Kelvin is fine. All right, so those formulas would be great additions as well, just so you have them. Now, this is powerful enough that we can use it to find other things other than just these four variables, because we know that the number of moles over here, the number of moles equals mass divided by molecular weight. So if that's true, we can put this in for N. So that would give us PV equals mass times RT over the molecular weight. Now, if we solve that to make it more useful, we can solve it for the molecular weight. Molecular weight equals mass times R times temperature over pressure times volume. And that can become very helpful, so it helps you identify what gas it is. And when you do that, the units should be, the units for molecular weight are going to be grams per mole. Now that means that the mass has to be in grams. Another little unit, and sometimes you have to worry about milligrams. Milligrams divided by 1,000 equals grams. More often, you will need kilograms times 1,000 equals grams. So both of those are probably going to be handy at some point, again, if you're not as adept at going from one metric unit to another. All right, we can also use this. Sometimes it's important we want to know how much we have, what mass there is, so we can solve it for mass. Oops, picked the wrong one. So that's another one. Mass equals molecular weight times pressure times volume divided by RT. When you put these in your calculator, something I should say, when you put it in the calculator, either you can take this times this times this, and then when you divide it by, make sure you use parentheses, divided by parentheses, R times T. And I don't think you really have to close the parentheses, but you can, and that'll work. Or you can do this times this times this, divided by R divided by T. But if you say you're going to divide it by R times T, that's actually going to put the T up on top. Your calculator is thinking that's what it is. So use the parentheses or divided by R divided by T. Either way will give you the right answer. And this unit will come out in grams. All mass will when you come out, because that's the unit that's in, comes out when we do the moles out of the R. The moles are going to be in grams. All right. More stuff that we can get from the ideal gas law. We know that density equals mass divided by volume. Therefore, we can if we find this formula, which is still just the ideal gas law that has M and MW instead of N there, I can take mass divided by volume on one side, move everything to the other side, and, well, first of all, probably want to write down anytime you have densities for a gas, it's going to be in the units grams per liter. Don't want to lose those points, so write that down beside density, put the units grams per liter, just like molecular weights grams per mole. Now if we solve that for M divided by V, so we just move this and this on one side and move everything to the other side, we get molecular weight times pressure over RT, which instead of mass divided by volume, you can just say that that equals density, and so you can just put that down. Density equals molecular weight times pressure over the gas constant times temperature. And these are all just tools that we're putting into your toolbox, your formula list, so when you go through to do problems, it's not hard. Just write down what you know, what it is that you're looking for, and then find the best tool that you have. You should have a tool for everything. We're going through enough of them that for now you should have a formula for each one that you have to look through, or that you have to find. Just look through until you find the one that will fit the what you know and what you're looking for. There is one specific case where that last formula is always going to work. You can always find density that way. But at STP, there is a shortcut. So I'm going to give you the shortcut because it saves a lot of time. And if we're solving for volume at STP, if you take any gas and you put in for 1 mole at STP, and STP, remember, is 1 atmosphere or 760 torr, and 0 degrees Celsius, 273 Kelvin. If you have 1 mole of that, of any gas, doesn't matter what gas it is, 1 mole of any gas at STP, I probably should put that in there. One mole of any gas at STP has a volume of 22.4 liters. Now that's, especially for the gases we're going to use, this is correct. When you get to college, if you go on in chemistry, you're going to learn that it's 22.414 for ideal gases. It'll give you 5 significant digits. But then it starts to vary depending on how ideal that gas is, what the interactions are, what the temperature, what the pressure is. But for what we're doing, 22.4 is going to be a good estimation of what it's going to be. So 1 mole of any gas at STP has a volume of 22.4 liters. That's handy to know. All right, now using that, if we want to find the density at STP, density still equals, it always equals mass divided by volume. But if we're going to do this at STP, we're just going to solve it for 1 mole. Doesn't matter how much they say that you have, because density doesn't depend on the size of the object. Remember, if you were here your freshman year when we had the King's Ransom, all of that gold, and you had to find the density. It didn't matter if you were finding the density of a big portion of that material or a small portion of that material, it's going to be the same density. So it doesn't matter what you're going to solve for. We're just going to solve for 1 mole. The mass of 1 mole will be just right off of the chart, just right off of here. And if you lose this, you don't have one underneath the document on under chemistry, one of the things that's listed there, there is a new table, and it's short. If you want to print it, you don't need a legal size. It will print onto a normal letter size paper, and it's a little bit more exact. I think they all go to at least 5 significant digits, maybe more on some of them, but it's still going to give you the same values to the significant figures we're doing. But the molecular weights on here, or the atomic weights on here, give you the mass of 1 mole. So we just have to look up what that is. And the volume, we just learned, for 1 mole at STP is always 22.4. So our formula simplifies for density. Now this is only at STP. Density just equals the molecular weight, which is what it adds up to on here, divided by 22.4. And this will be in grams per mole divided by liters per mole. The moles you invert and multiply. The moles will cancel, and you'll end up with grams per liter, which is always the unit for density of a gas. All right. Remember that gram molecular mass is the same thing as molecular weight. That's just another term for exactly the same thing. Gram molecular mass, molecular weight, and from over here, these still work. The number of moles equals the number of objects divided by Avogadro's number. So if we're talking about atoms, molecules, or formula units, anytime it says how many molecules, how many atoms, how many formula units, you're going to have to use this formula. And you might have to rewrite it for you're going to solve it for this. And the capital N, remember, is 6.022 times 10 to the 23rd. So if you were looking for the number of objects, that's just going to equal the number of moles times how many are in a mole. So hopefully you already have that down as one of those, but again, some of you are not as friendly with algebra as you might want to be. That might help you out in that as well. Now you're going to do 2 assignments this week, just 2. And the first one is in textbook, and you can download the answer sheet on the chemistry webpage. And it will be week 2 textbook assignment. And you're going to do 9 through 14, but you aren't going to do 10 and 12. You can do 10 and 12. I mean, you have the information there. It's just that usually there are enough questions about how it's worded that it's one of those where I come around and I just explain a little bit and, oh, I get it. But since I'm not there, I don't want to confuse you. It's just not going to be worth you trying to figure out what that wording, what it actually means. So just skip 10 and 12. Now, that leaves, this is 6 questions, and I'm taking 2 out, so there's only 4 questions. In honesty, I will tell you that there are some A, B's, and C's, but one of these has A, B, and C in it as well. So it's more than 4, but it's not that many. I'd like you to have those done by Wednesday at noon. And I will check them, and I'll give you a grade. Now, it's hard for me to send it back, and on this it'll probably be easier. So after noon on Wednesday, I'll post an answer key showing my work, and I'll try and do it as clear as I can so you can see exactly how I did it. And so if some of your answers are different, you can see where you went on a different path. But that's also why I want it by noon. Once I put this out, then it's not so much of an academic task to get the right answers, because you just have to click on a button and all the answers will appear there. So make sure you get this done by noon, and then now you can start working on assignment 2 at any time. You don't have to wait until I put the key here. But I wouldn't turn this in until you see, turn this one in until you see the key, so you don't make the same, the whole point of this is don't make the same mistake. If you made a mistake up here and oh, that's what you do, then don't make that same mistake on this one. All right, remember on Thursday we'll have Zoom time where you can ask me questions, either on exactly why did I do this, or a question on there as well. So I hope this distance learning is working for you. I hope we can get through a few more weeks of this. Next week we will talk about stoichiometry. We'll go to stoichiometry in gases, and that's going to use what you know about stoichiometry. It's going to use the ideal gas law, and some of it will seem a little bit more complicated. Some of it will actually seem a little bit easier than what it did when we just did the regular stoichiometry. But next week will be stoichiometry. So I hope this goes well for you.